Hi students, we are going to discuss the dependence of photoelectric current on the applied voltage. So for this we have to keep the frequency and intensity of light as constants. So I will keep the frequency, okay, frequency is constant and the intensity initially I will keep the intensity as I1. Okay, I1 is kept constant. So how to maintain the intensity as constant? I told you, keep the source fixed at the same distance. Okay, now keeping the frequency and intensity as constant, so what is to be varied is the applied potential difference between the cathode and the anode, or the potential of the anode can be varied in steps. I told you that this anode potential can be kept positive with respect to the cathode, or zero voltage, or negative with respect to the cathode by using a commutator or another switch. I told you, potential divider or voltage divider. So either commutator can be used or potential divider or voltage divider can be used, so that any desired value of positive, negative or 0 volt can be applied to the anode, which is the collector plate. Okay, at present this positive potential is connected to the anode. When ultraviolet radiations of a certain minimum frequency called threshold frequency and above than that is incident on the emitter cathode plate, photoelectrons will be emitted as usual. Since these electrons are negatively charged, they will be attracted towards the positive potential of the anode, and they constitute a photoelectric current that can be measured by the microampere meter. Then slowly I will reduce the positive potential applied to the anode from a positive maximum to 0 up to 0, so that what will happen, even when 0 voltage is applied to the anode also, some photoelectrons having the sufficient kinetic energy, they will manage to reach the anode, and hence a photoelectric current will be produced. Okay, after this what I am going to do is very important. By reversing the polarities of anode and the cathode, by using a commutator or a voltage divider, I will apply a negative potential to the anode with respect to the cathode. So what will happen? Naturally, when negative voltage is applied to the anode, the negatively charged electrons will be repelled back. But completely all the electrons will not be repelled back. This is because all the electrons emitted by the cathode plate do not have the same velocity. They all do not have the same kinetic energy. So it ranges from a minimum to a maximum. So even when negative potential is applied to the anode, the photoelectric current does not drop to 0 immediately. Some few electrons will be there having the sufficiently high kinetic energy. They will reach the anode now also. So they constitute a current. Okay. Now what will happen if I go on increase the negative potential from 0 to -2, -2 to -4, -4 to -6, more and more negative if I will apply, more and more repulsion will be experienced by the photoelectrons. So one stage will come that not even a single photoelectron can reach the anode. Such a negative potential applied to the anode will repel the electrons back to the cathode. For example, let us say it is -12 volt. For example, I said. So when I apply -12 volt, what do you mean? No single photoelectron is able to reach the anode. So what should be the current in the circuit? It must be 0. Okay, at -12 volt itself, the current has become 0, I say, for example. What will happen if I go on increase beyond -12, like -14, -16 up to -20 volt? Already the electrons are unable to reach the anode. Then what is the use of increasing beyond -12? So which is the minimum negative potential required here is minus 12. This minimum negative potential applied to the anode to stop the most energetic photoelectron such that the photoelectric current in the circuit becomes zero is called as stopping potential or cut-off potential. Both are one and the same. Okay, students. So now what is meant by stopping potential? So this is a new definition we are learning now. This stopping potential also is called by another name, that is called as the cut-off potential, and that is denoted by V naught. Okay, how do you define this stopping potential? This is defined as the minimum negative potential. Okay, simply negative potential we cannot mention because beyond minus 12, minus 14 also is negative, minus 24 also is negative. But which is the minimum negative potential or minimum retarding potential required to stop the electrons only is called as the stopping potential. So we have to take care. This word minimum has to be highlighted. So the minimum negative potential. Okay. This is applied to the collector plate, that is anode. So this is the minimum negative potential applied to the collector, that is anode. Okay. What for we are applying this? To stop the most energetic, photoelectron also. So to stop the most energetic photoelectron, which is having what? Maximum kinetic energy. That means its kinetic energy is K maximum. Okay, the kinetic energy of the fastest photoelectron is denoted by the symbol K max. That is kinetic energy maximum. Even that photoelectron also will be stopped at this negative potential. Okay, students. Now I am representing this on the graph. Initially I told you for a given frequency, how will you keep the frequency as constant? The same source must be used. Same source. How will you maintain the intensity as constant? The source should be fixed at the same distance. Okay. So initially what intensity I have chosen? I1. Okay. Next I will repeat the experiment by keeping some other constant intensity I2, which is greater than I1. Okay, students, because I want to see the dependence of this stopping potential with the intensity of light also. That is why next time when I do the experiment, frequency is kept constant and the intensity I2, some other value greater than I1 is fixed as constant. Third time when I do, again the same frequency is kept constant, but some other higher intensity, that is I3, which is greater than I1 and I2, I will fix that as constant. And when I plot the graph by taking the voltage, applied voltage or anode potential along the x-axis and the photoelectric current, okay, this is the photo current, okay, this is the photo current along the y-axis. So what is the nature of the graph I am getting? You see, initially when you do with the fixed intensity I1, okay, when the anode potential was increased from 0 to a maximum. So initially what has happened to the current? You see, up to this point, from here the current has increased, and beyond that if I change the voltage, the current is remaining constant. This constant current only is called by the name saturation current. Okay. So the current has attained a saturation, maximum constant it is. Then again I reverse the voltage in the negative axis. So on the right side, positive x-axis, positive potential applied to the anode is represented. Then on the second quadrant, that is on the negative axis, okay, you see that negative voltage is represented along the negative x-axis. Okay, students, so both the first quadrant as well as the second quadrant are being utilized here. So the graph very clearly indicates when I1 intensity was kept constant and the potential difference between the anode and the cathode is varied. So what happened, you see here, after beyond 0, when the negative potential is applied, means the current decreases, and then finally you see that the current has become 0, photoelectric current has become 0. Understand? That means at this potential, negative potential V0, some books they are representing as minus V0, but V0 is enough, okay. So V0 is called the stopping potential. So this V0 only is called as the stopping potential or cut off potential. At this negative voltage, the photoelectric current in the circuit is equal to 0. At this potential, the photoelectrons will not reach the anode. They will not reach the collector plate. That is why the photoelectric current is equal to 0. Okay, my dear students. Now, initially, the fastest electron was able to reach the anode even when it was having a 0 potential. But that fastest photoelectron also is now unable to reach the anode for this potential. Therefore, the kinetic energy of the fastest photoelectron, half mv square maximum, must be equal to the work done to stop the electrons, is it not, with the maximum kinetic energy. Therefore, this must be equal to the charge of the electron into applied potential. Understand? Because this fastest photoelectron also is stopping now. At what potential? At a potential V0 applied to the anode. Therefore, E into V0 must be equal to the work done to stop the most energetic photoelectrons. And hence that must be equal to what? Half mv square maximum. Therefore, V square maximum is equal to what? 2E V0 divided by m. Okay. So this implies what is V maximum is equal to, V maximum must be equal to what? Square root of 2 into E V0 divided by m. Okay, students. So this equation is very important. On the right hand side of the equation, what are the terms you see? 2 is a number which is constant. E is charge of the electron which is constant. M is the mass of the electron which is also constant. Therefore, V maximum, okay, is equal to square root of 2 EV by m into square root of some constant multiplied by V0. So, if I will substitute the values, it is coming as 5.93 into 10 to the power of 5 into square root of V0. So, V maximum is proportional to square root of the stopping potential. So, this is a very, very important equation. This expression is very important to solve the numerical problems. Suppose, for example, if the velocity of the photoelectrons is doubled, means then what will happen to the stopping potential? Like that, some interesting questions have been already asked in the IIT and the NEET. I hope you must have understood. Now I am going to summarize. What is more important is, who is providing the kinetic energy to the photoelectrons? We studied that when photons are incident, when light is incident on the metal plate, electrons are emitted. So when the light itself is having less energy, means the kinetic energy of the electrons also will be very less. When the incident light is having extremely greater energy, then the photoelectrons will pick up more energy and have more kinetic energy. Is it not? So the kinetic energy of the photoelectrons, depends on the frequency. Oh, so my dear students, this kinetic energy, okay, kinetic energy maximum is proportional to the incident energy. The incident energy is what? H into nu. So I can write this is proportional to the frequency. Therefore, stopping potential also is directly proportional to the frequency. In this graph, what is very clearly visible to us for different intensities I1, I2 and I3, such that I3 is greater than I2 is greater than I1. For any intensity, the stopping potential remains the same. It is found that the stopping potential remains the same irrespective of the intensity. Why? Because the stopping potential, see, for example, if you want to stop your vehicle, say train has to be stopped, a car has to be stopped, a two-wheeler has to be stopped. For which of these three very strong brake is required is for the train, because its kinetic energy will be more than the kinetic energy of the car and the cycle. So the braking force depends upon what the kinetic energy. So my dear students, what you must understand from the graph is the stopping potential is independent of the intensity of the incident radiation, but it depends only on the kinetic energy of the photoelectrons, which once again depends on which factor? The frequency or the energy of the incident radiation. I hope you must have understood. Shall we go to the next topic? Okay, bye.